So what we're going to do today is to talk about maximums and minimums. So let's start out. We're going to start out with talking about an absolute minimum and an absolute maximum, and then we'll move on to talking about what we call relative minimums and relative maximums, and then we're going to talk about how it is that we actually go about finding minimums and maximums. All right. So we'll start out with a definition, okay? And the definitions inside of this particular in this particular section are really important. Okay, because they help us to define what it means to be the things that we're going to be looking at. So you really do want to make sure that you know your definitions. So let's start out with this definition. Let C be a number in the domain D of a function f. Then f of C is the absolute maximum value of f on D if f of C is greater than or equal to f of x for all x belonging to D. And an absolute minimum value on f on D if f of C is less than or equal to f of x for all x belonging to D. Okay. Now, what we want to do is we want to kind of understand what this definition means, and so let's actually look at that. Okay. So we'll start out and let's take a look at a graph. And let's take, for example, we'll look at this one. It's a parabola. Okay. This parabola here, and let's say, for example, this is f. So this is f of x. And we want to say that we want to define, we let D equal all real numbers. Okay, so D is all real numbers. Okay, then our C is this value right here. Okay, this is C right here. Okay, and so f of C, okay, is the absolute maximum on D. So that's actually the first one. So it's kind of intuitive. Absolute maximum. It's the very biggest point, right? Or very largest value, okay, for all the values for everything inside of the domain being all of R. But let's say, for example, that we change our domain, okay? Let's say now that we take our domain, we're going to let our domain equal, okay? We'll let our domain equal just 0 to infinity now. Okay, 0 to infinity. And now if you look here, okay, so this value C is actually less than 0. So at 0, we're going to end up having our absolute maximum, right? Because after 0, it just keeps the function decreases. So consequently, our f of 0 is the absolute maximum on 0 to D, or 0 to infinity, excuse me. Okay? Now what about the absolute minimum? Well, if we look here, going 0, we're just going to keep descending, right? It keeps going lower and lower and lower and lower. So in this case, there is no absolute minimum on 0 to infinity. But what if we change our domain again? Let's say, for example, we take our domain, we make our domain now 0 to 5. Okay? From 0 to 5, now our absolute maximum, f of 0, that's going to be our max, our absolute maximum. And our minimum now, okay, if we look, let's say, for example, that 5 is right here, okay? So it turns out that f of 5 is now my absolute minimum on this particular interval, okay? So the big thing to get here is the absolute minimum and absolute maximum are really dependent upon the domain. Now let's look at a second definition, and this second definition is going to be for a local minimum or a local maximum. And what we're going to do is we're now going to introduce another term too here, and that is extrema. Okay? Extrema is just a shorthand way of calling maximums or minimums. So it refers to either one of them. Okay? So I'm going to be using that term. You're going to see that term. So we can call that maximums or minimums for the extrema. Now, we look at here, the number f of c is a local maximum value of f if f of c is greater than or equal to f of x when x is near c. And local minimum value of f if f of c is less than or equal to f of x when x is near c. Okay? We should actually define what it means to be near c. To be near c is within an open interval around that value. And so when we talk about an open interval, the difference here is going to be that our absolute minimums and our relative minimums and relative maximums, or our local maximums, local minimums, right, are actually sometimes they may be different from what our absolute minimums and absolute maximums are going to be. Because absolute maxes and absolute minimums do not require this open interval around the object. And so let's actually talk about this. Let's take an example to see this. Now, I should also say one other thing is another way to talk about relative or local equals relative. So I'll use that term relative as well. So relative extreme. So let's look here. Okay, we'll look at this particular graph. All right, and so if I look, my absolute minimum, my absolute max, right, the highest value on this for this entire domain is going to be f of -1 equal to 37. Okay, because that's clearly the tallest point. And my absolute minimum is going to be f of 3 equal to -27. That's my absolute minimum. Okay. Now what we want to do is we want to determine what our relative minimums and relative maximums are. So if I look here, one is to notice that for -137, there's not an open interval around -1. Okay, so since there's no open interval, right, there's nothing to the left of -1, right? It's all closed. So for example, -1 to our entire thing, 4, that's called closed, all right? Okay, we don't have anything that is less than -1, so no open interval around -1. Same can actually be true for 4 as well, okay? There's no open interval around 4, and so consequently, we're not going to be able to have relative extrema there either. So there's no open interval around 4. Now let's talk about relative extrema, or local or relative extrema. So if I look here, you kind of see them. You can look at them. So for example, f of 1, which equals 5, all right, is a local max, right? Everything around that point is going to be less than it, right? And we can construct an open interval around around 1. So because we can construct an open interval around 1, it's possible for 5 to be the local max. Same thing down here with 3. Now in this case, f of 3 equal to -27 is also a local min. So it's going to be a local minimum. So in this case, what you can see is that we could actually have an absolute minimum and a local minimum be the same. So it's possible that local mins, local extrema, are also absolute extrema. And that's going to be kind of handy for us later on. So we've got that it's possible. So let's kind of review what the basic idea here is. An absolute maximum is the very highest point inside of any domain. So that's our absolute max, and it doesn't matter whether or not it's an open interval or not. Absolute minimum, the very lowest point inside of the domain. Okay? Local ones are ones that basically, they're kind of like our little peaks, or there are little valleys, okay, inside of our graphs, and so consequently, we kind of, we want to eyeball those, or we're going to find out a way to find these later on as we do more calculus, okay? And then remember that it is possible that local extrema are also absolute extrema. What this now gives us is this idea of the extreme value theorem. And it's kind of intuitive. If you think about it, it's very intuitive. If f is continuous and on a closed interval a to b, then f attains an absolute maximum value, f of c, and an absolute minimum value, call it f of d, at some numbers c and d in a to b. Okay? So as long as the function f is continuous, right, and we've got a closed interval a to b, then what we've got here is we've got, that a, but somewhere between a and b, we're going to get some kind of absolute max and some kind of absolute min. All right? And so in this case, for number 1, what we can see is that, in fact, they're exactly at the places that we think they are, right? Top of the hill, bottom of the hill. Now for 2, what we get is that C, again, it's the top of the hill, that's our absolute max, but D now, which is the end of the interval, is going to be our absolute min. And that's going to happen all the time, right? Say, for example, if you have something that's continuously decreasing, right, that never stops decreasing, right, or it never stops increasing, then your endpoints are going to be your highest and your lowest points. And then we look here, and what we can see is that you actually have 2 absolute maximums and 1 absolute minimum. It just says, this theorem just says that it attains an absolute maximum value, right? And it attains an absolute minimum. It doesn't say how many. We could have actually multiples. We could have many, many of them. Say, for example, for a sine function, you're going to get a lot of different maximums and minimums. So, consequently, you just want to pay attention to that. Okay? But that's what this extreme value theorem is saying. That we will always have either an absolute minimum, or we will always have an absolute minimum and an absolute maximum on any closed interval. So now we want to ask the next question: how do we find calculus to find, how do we use calculus to find the relative extrema? So we'll start out with this definition. A critical number of a function is a number C belonging to the domain of f such that either f prime of c equals 0 or f prime of c does not exist. Okay? And then we have the second theorem: if f has a local maximum or minimum at c, then c is a critical number of f. Okay? So notice what this is telling me is that if f is a local maximum or minimum at c, then c is also a critical number of f. All right? And that's going to be the way that we're going to actually determine whether or not we have a max or a min. Okay? So let's take a look at this and let's discuss this for a moment. Okay? We'll look at this and we'll say, let's say we have a graph. Okay? Right? And here's our graph. And let's say we have, and there's our function. We have an asymptote. Say we have that asymptote here at 6. Okay? And we have, we'll see, a relative min at 3 and a relative max at 1. Okay? And then we'll have no local minimum or local maximum. All right? So when we look here, what we want to notice is that at these relative extrema, right, the graph has a tangent line, okay, has a tangent line, a horizontal tangent line. So it's got horizontal tangent lines. And same thing down here at the bottom, okay, at our local maximum. And if we have a horizontal tangent line, what that means is the slope of the tangent line is equal to 0. Okay, so slope equals 0. And we know that that's equivalent to saying that f prime of 1 is going to equal 0. And, again, that f prime of 3 is also going to equal 0. Okay? Because the tangent lines at those 2 points are actually going to be horizontal. Then we also have, a place where the actual function is undefined. So at 6, the function is undefined, so it doesn't have a derivative there. So no derivative. Sometimes we might, okay? We might have a function that is defined at a particular point but doesn't have a derivative. We saw that, for example, with the absolute value, okay? But this one here, what we see here is we have 3 critical values. We have 6, 1, and 3, okay? Those are our 3 critical numbers, okay? Excuse me, critical numbers, right? We have, that's a critical number at 6, critical number at 1, and another one at 3. These are going to become actually really crucial as we start graphing functions and we start doing real analysis of functions utilizing their calculus. All right. Now we kind of got an idea that if we happen to have relative extrema, okay, that their derivative is going to end up equaling 0, right? And so consequently, local minimums, local maximums, their critical numbers are going to be 0. They're going to be critical numbers, excuse me. Their derivatives will equal 0. However, it is not true, okay? It is not true that a value c such that f prime of c, excuse me, equals 0 is always a relative extrema. So there are examples, and we'll take a look at one. There are examples in which this is not true, okay? So we want to get that just because the derivative at a certain point, say, for example, the derivative at, let's say that the derivative at 5 was actually equal to 0. Does that necessarily mean that it's a local minimum or maximum? The answer is no. It doesn't actually. So let's take a look at an example. We'll use x cubed as our example. So I come through here, right? Okay. And here's what x cubed looks like. And here, all right, if f of x equals x cubed, right, then f prime of x is going to equal 3x squared. Okay, so 3x squared equals 0 at x equal to 0. So it actually does end up having a horizontal tangent line there. Okay, our problem is, though, is that, but x equals 0, okay, is not, or in this case, it would actually be f of 0 equal to 0, is not a relative extrema. So we're going to actually have to do some testing. We're actually going to have to figure out if this is true or not. Okay, we're going to have to figure out, all right, when is a certain set of, when is a value actually going to be a relative minimum or relative maximum, all right? But at least we know now that we can look at places, right? Okay, we can look at places that have horizontal tangent lines to see that they might be relative extreme, right? They don't have to be, but they might be. So let's take an example, and let's find the critical numbers for f of x equals 2x cubed plus x squared plus 2x. All right. So what we know is that f is a critical number, or excuse me, f prime of c is a critical number if f prime of c equals 0 or f prime of c does not exist. Okay. So when I look at this, what that means is that I'm going to take the derivative. So f prime of x is then going to equal 6x squared plus 2x plus 2. Then what I'm going to do is I'm going to set it equal to 0. So 6x squared plus 2x plus 2 is equal to 0. Okay, so that then, if I factor out, that'll give me x squared plus x plus 1 is equal to 0. Okay. And so consequently, that now, excuse me, what am I doing? That's 3x squared plus x plus 1 is equal to 0. All right. And so now what we want is we want to say, okay, well, that if I divide by 2, that means that 3x squared plus x plus 1 is just equal to 0. So we multiply by 1/2 on both sides. Now that doesn't look factorable, but we could probably use the quadratic. Okay, so I'm going to use the quadratic equation. And so I'll get a equal to 3, b equal to 1, and c equal to 1. Okay, so what I get now is I get negative 1 plus or minus the square root of, and this will be 3, excuse me, not 3 squared, but 1 squared minus 4 times 3 times 1 divided by 2 times 3. Now what we notice is, notice 1 minus, and this will be 12, 13. 1 minus 13 is equal to negative 12. Okay, so, right, what that tells me is that there are no real values of x where f prime of x is equal to 0. Okay, we end up with a complex number, so we end up with no real values of x where f prime of x is equal to 0. Well, what does that mean? That actually means that we don't have any critical numbers because we have one other fact, okay? A polynomial, which we have here, okay, is differentiable everywhere. So f has no critical values, or no critical numbers, excuse me. And there we go. So what we did here is we said, okay, well, polynomial is differentiable everywhere, so I'm not going to get any, like, not exists. F prime of c does not exist, right? And I have f prime of c equal to 0. Well, I just showed that, in fact, f prime of c is never going to equal 0. By the way, this is actually 1 minus 12, which is equal to negative 11, okay, just for the sake of clarity and consistency. But basically, that's the idea, right? We look and we ask, well, is the function differentiable, is not differentiable somewhere, right? Is there a problem point? So I sawtooth, say, for example, we have an asymptote, right? Okay. Or is f prime of c equal to 0 at any place? All right. So let's take a look at another one. So let's take a look at another example. Let's find the critical numbers for h of x equal to x minus 1 over x squared plus 4. Okay, so what we're going to do with this is we're going to say, all right, so I first, right, I want to figure out, well, one, if I notice, x squared plus 4 will never equal 0. So, all right, it appears at least that we're differentiable everywhere. So there is no place where f is undefined, where h is defined. Excuse me, where h is undefined. So that's our first place that we want to look. So now what I'm going to do is I'm going to take h prime of x. So h prime of x is going to equal, and this will end up giving me, this will be 1 times x squared minus x squared plus 4 minus, okay, 2x times x minus 1 all over x squared plus 4 squared. Okay, this will then equal x squared plus 4 minus 2x squared plus 2x divided by x squared plus 4 squared. Okay, and this will then equal negative x squared plus 2x plus 4 divided by x squared plus 4 squared. And so that's my derivative. All right. Once again, notice that x squared plus 4 is never going to equal 0. So the function appears to be differentiable everywhere as well. The function is differentiable everywhere. So the derivative exists on the real line. So the derivative exists on R. Now we want to figure out where is h prime of x equal to 0. Well, we don't have to worry about the bottom, but the top we will. So let's take that. Let's find negative x squared plus 2x plus 4 equal to 0. Okay, to find our critical numbers. And so what we'll do now is I'm going to factor out a negative 1. Right, so we'll make this negative 1 times x squared minus 2x minus 4 equal to 0. Okay, so that means that x squared minus 2x minus 4 has to equal 0. And for the sake of a's, I'm just going to use the quadratic formula again. So this is going to end up giving me 2. So x will equal 2 plus or minus the square root of 2 squared minus 4 times 1 divided by 2 times 1. And that's actually a negative 4, excuse me. Negative 4 times negative 4 plus 1. So this is going to equal 2 plus or minus the square root of 20 divided by 2. A little bit of algebra in here. We get 2 plus or minus 2 root 5 over 2. So what we get is that we get our critical values, our critical numbers, excuse me, are 1 plus or minus the square root of 5. Okay, those are our critical numbers. Now, while we may not be able to find whether or not something's a relative extrema or of some kind, we are actually going to be able to use that extreme value theorem in conjunction with what we learned about critical numbers to find absolute minimums and maximums all the time. Okay, so let's take a look at how we're going to do this. Right, it's very systematic, and as you do it a couple of times, you'll understand the method behind it. So first, we're going to find the critical values of f and a to b, and we'll plug them into f. All right, so we'll find it on the open interval a to b, so not a, not b. Then we're going to find f of a and f of b, so those are going to be our endpoints, because remember, we could have absolute minimums and maximums on our endpoints, so we got to deal with that. And then we compare the values from step 1 and 2. The largest of the values is the absolute maximum value, and the smallest is the absolute minimum value. Okay, so it's a 3-part process to find that absolute minimum and absolute maximum. All right, so let's take a look at how we might do that in an example. So let's find the absolute maximum and minimum for, and this is 5 plus 54x minus 2x cubed. All right, now again, we've got a polynomial here, so it's differentiable everywhere. And so consequently, there's no place in which we're going to have not a derivative not existing. So what we're going to do is we're going to find f prime of x, right? And that's going to then be 54 minus 6x squared. So what we'll do, this is our a piece. We're now going to set that equal to 0. So let's say let's negative 6x squared plus 54 equals 0. Okay, we'll factor out a negative 1. So that gives me 6x squared minus 54 is going to equal 0. Now, again, 6x squared is going to equal, and this will be 54. And I'll divide by 6, both sides. So I get x squared is equal to 9. So x, when I take the square root of both sides, is going to equal plus or minus 3. Now if I look at my domain. Okay, look at my domain. My domain up there is 0 to 4. So x equals 3 is the only possible extrema in the domain. Relative extrema in the domain. All right, we're not going to check negative 3. Negative 3 is not going to matter. Okay, all we're going to do is we're going to just check 3 because 3 is the one that's in the domain. So I take f of 3, and that's going to equal 5 plus 54 times 3 minus 2 times 3 cubed. Okay, so that's going to be equal to 113. Okay, so that's our first value. Now we go to B, and we're going to have to find f of A and f of B. So first, we'll find f of 0, because that's the left endpoint. Or excuse me, the right endpoint. F of 0, excuse me, the left endpoint, is going to equal 5 plus 54 times 0 minus 2 times 0 cubed, which just equals 5. Okay, so that's f of 0. And then f of 4 is going to equal 5 plus 54 times 4 minus 2 times 4 cubed. This equals 93. So now when I look at it, now I'm going to do part C. I'm going to figure out which one's the highest and which one's the lowest. Okay, so f of 3, which equals 113, is the absolute max because that's the very highest value in the interval. And f of 0, which equals 5, is the absolute min. So this method, it's very systematic. Okay, you're going to start out, you're going to go out and find your relative extrema. You're going to find all the places where f prime of x is going to equal 0, right? And then you're going to find the value for the function at that point. So what that's done is that's told you where is the tangent line horizontal, and then the idea here is that you need to find what the y value is for that point. And that's why you've got to plug in whatever your x is into the function in order to figure out what its y value is. Okay? The second piece here is to notice, all right, we're going to find the endpoints. So f of 0 and f of 4 in this case, right? And then we'll compare the three of them. You can see the biggest one, that's our absolute max. The smallest one is going to be our absolute minimum. And that's the closed interval method. Okay, so this completes the lecture on maximums and minimums. Big things that you want to get. Make sure that you memorize those definitions, that you really know what they mean and how they are different. Okay, what it means to be an absolute maximum, what it means to be a relative maximum, absolute minimum, relative minimum, and how are they different. Okay, then we also want to know this idea of the critical number, right? This is so fundamental to calculus. A critical number is where either the derivative equals 0 or the derivative does not exist. So those are going to be our critical numbers, all right? And you want to make sure that you know what those are. And then finally, we utilized this closed interval method in order to allow us to find that absolute minimum and absolute maximum. Key point, not the relative min or the relative max, just the absolute minimum and the absolute maximum. All right, this completes the lesson.